All right, we're about to enter into a really meaty subject, but this video was hopefully going to be pretty short, just kind of a real brief introduction to what we're really going to be talking about for the next term and a half, really, or term and a quarter, I guess. So keep in mind, right, what a carbonyl is. It turns out carbonyls have some really interesting but sometimes complicated reactivities, right? And so it turns out that that carbon is going to be something that is going to be able to be attacked because it's got a partial positive charge, and because of that it is electrophilic, and then also this oxygen has a partial negative charge. The interesting thing about the way that carbonyls react, to begin with, it's going to depend on some sort of nucleophile. And it turns out that that nucleophile is attracted to that positive charge of the carbon, which causes a movement of electrons, kind of like that. Now, the one thing that makes it kind of interesting is even if we're only limiting our discussion to this kind of attack, it can attack in, a type of nucleophile can attack in base, obviously. I have a really decent nucleophile with a negative charge, right? A lot of them can just go ahead and attack that carbon directly. It also turns out there's a whole nother classification of carbonyl reactions that are acid catalyzed. In other words, we're going to protonate that oxygen and then cause that carbon to be attacked by an even weaker nucleophile, right? And we've kind of seen that kind of thing before. What is going to be different about the way that carbonyls can react is, first of all, depending on what's bonded out here, let's just use an X, we can either keep that X present, which is going to be called a carbonyl addition reaction, or that X could actually leave, and that would be called a carbonyl substitution reaction. And it is true that usually additions will occur or substitutions will occur depending on what kind of carbonyl you're talking about. Where we're going to see the majority of carbonyl additions are with our first subject, which is going to involve ketones and aldehydes. And of course, I probably don't need to tell you this, but ketones are when we have a carbonyl with just a normal aliphatic carbon on either side, or we have aldehydes, which react a little bit more quickly, where we have an H on one side. Carbonyl substitutions are going to happen with carboxylic acid derivatives, and we're probably not going to get to that this term, but next term is going to begin with them. And carboxylic acid derivatives, there's really 5, you could even consider there to be 6 different carboxylic acid derivatives. They're all going to have very, very similar parts to the ketone aldehyde carbonyl additions. It's just that in the end, we're going to actually substitute that group for that particular nucleophile. Now, if that was all there was, our lives would be so much easier. But it turns out there's a whole nother type of chemistry associated with these that, I'll be honest, really confused me the first time around. So we're really going to kind of slow down when we get to that in third term. And that has to do with if this R happens to have any kind of hydrogen, right? And this position is usually given an alpha, right? That's the alpha carbon. And so a whole other type of chemistry which can actually compete with both of these is going to be alpha carbon, we'll just call it chemistry, right? In other words, instead of having a nucleophile, which is, by the way, usually a really good base attacking that carbon, there's kind of this competing reaction where that nucleophile comes in and acts as a base, causing a flow of arrows that looks very similar to that. And that species right there, where there's a, if if this had an H to begin with, that would be called an enol. If there was no H out there, this would be called an enolate. This is also considered enol-enolate type chemistry. And the interesting thing there is that species itself can serve as a nucleophile and do carbon-carbon bond forming reactions, right? So there's a lot going on here when we get to this alpha carbon chemistry. What we're going to concentrate on in the next couple of weeks here is really getting a really good handle of when carbonyl additions are going to occur. And I'm going to kind of purposely choose systems where we don't have to worry about this as a complicating factor. Similarly, when we get to the carbonyl substitution in third term, we're going to talk about these things and pretty much ignore alpha carbon chemistry. And then once we're really solid in the rules for these two things, we're going to kind of see what we can do to make this alpha carbon chemistry a little bit more likely. So there'll be a little bit of hand waving, but I think it'll be a pretty fun ride. And the thing that really made me interested in these types of reactions is that this is really the chemistry that goes on in any kind of biological system. Usually when you're forming carbon-carbon bonds in the body and things like that, you don't have really strong nucleophiles, right? Because a strong nucleophile would pretty much be protonated right away and probably end up in you becoming a big pile of mush, right? And so these types of reactions are reactions that you're going to see all over biochemistry. So stay tuned.